Hello, students. So today I'll be talking about the giant Rydberg atoms and how in our lab we tame this giant Rydberg atoms. And I'll talk about how we are developing quantum technologies via quantum control of this cold Rydberg atoms. So the outline of my talk is I'll give an introduction to quantum technologies with ultra-cold atoms. And then I'll talk about transition frequency measurement of this highly excited Rydberg states. And then I'll talk about our recent result on Doppler-enhanced quantum magnetometry with Rydberg atoms, how we do quantum sensing with this Rydberg atoms. And then I'll talk about how we observe Rydberg excitation in cold atoms. And thereafter, I'll talk about the effect of interatomic interaction in cold Rydberg atoms, which is very important for quantum technology applications. And then I'll talk about a few of the future perspectives, what we are planning to do with this cold Rydberg atoms, like scalable quantum network and quantum sensing with tweezer arrays of single Rydberg atoms. So Rydberg atoms are atoms where the electron is excited to very highly excited state. And that's why the size of these Rydberg atoms are extremely large. And hence they're called the giants of the atomic world. So Rydberg atoms were first discovered by Johannes Rydberg, who found an empirical formula linking the various wavelengths of the spectral lines observed in alkali atoms. And this discovery played an important role in the birth of quantum mechanics. So let me talk about what is quantum technology. So acquisition, storage, in transmission and processing of information using quantum sensors, processors, and transmitters is called quantum technology. There are various regimes of quantum technology, like quantum computation, quantum communication, quantum simulation, and quantum sensing and metrology. So as I said, because of the electrons being excited to very highly excited Rydberg state, Rydberg atoms have a lot of exotic properties. For example, as I mentioned, Rydberg atoms have large size. They are giant atoms. And the size of the Rydberg atoms goes as n square, where n is the principal quantum number to which the electron is excited to. And so since they're giant atoms, they're ideal for exploring mesoscopic quantum regime. And they have a very long lifetime, and which goes as n cube. And this gives long coherence time to Rydberg atoms for quantum technology applications. And Rydberg atoms have large polarizability. That means a very large response to external electric fields, both DC and AC, and it goes as n to the power 7. And hence, Rydberg atoms are extremely sensitive to small DC or AC electric fields. And hence, Rydberg atoms are very promising for doing quantum sensing and metrology with Rydberg atoms. And Rydberg atoms have a very large interatomic interaction. For example, it has large dipole-dipole interaction, which goes as n to the power 4. And it has a very large van der Waals interaction, which goes as n to the power 11. So it's very strong interatomic interaction. And so the consequence of this large interatomic interaction is that we can create quantum entanglement of two Rydberg atoms. And this quantum entanglement is created via Rydberg blockade. And this can lead to fast quantum gates for quantum computation. And then we can do quantum simulation of condensed matter systems using Rydberg atoms. We can do quantum simulation of the many-body physics in condensed matter systems. And finally, we can use Rydberg atoms as a very deterministic single photon source um, for quantum communication. So you can see that Rydberg atoms are a very versatile system, and this can explore all the regimes of quantum technology. So as I talked about quantum entanglement with Rydberg atoms, um, so this at the heart of quantum entanglement with Rydberg atoms is the phenomena called Rydberg blockade. For example, if you have two Rydberg atoms very far away, they are not interacting. But as you bring the another atom close to the Rydberg atom, because of this large dipole-dipole interaction, there is an energy level shift of the other atom. And the laser which is exciting one atom to the Rydberg state, because of this energy level shift, cannot excite the other atom to the Rydberg state, and vice versa. So you can see that there is a correlation which has formed because of prevention of excitation to the Rydberg state because of the energy level shift, and this leads to the creation of entangled state between these two Rydberg atoms. So the fact that quantum entanglement is at the heart of, and it is at the center stage, is evident from the fact that the Nobel Prize in Physics 2022 was awarded jointly to Alain Aspect, John F. Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So quantum entanglement is really, the very important phenomena which is, at the heart of quantum information science and quantum computing. So, what is the advantage of cold atoms in building the quantum processors or quantum computers? So, cold atoms are highly coherent system because of the ultra cold temperatures, and because of the cold temperatures, the quantum regime becomes easily accessible because lower the temperature, larger is the de Broglie wavelength, and more you're in the quantum regime. And these Rydberg atoms have very high degree of controllability, and at very fast time scale, you can control any parameter in the system, just as you're controlling the parameters in a numerical simulation. The difference is that you're actually controlling and doing simulation or quantum simulation on real atoms. Also, you have complete control of the interatomic interaction, which gives rise to quantum entanglement. And also, you can completely control the temperature, the dimension, the atomic spin states. And using this completely controllable system, we can explore the various regimes of quantum technology. So this is our Rydberg experiment group at RRI, at Raman Research Institute. So we have 5 very enthusiastic PhD students, and the senior most PhD student, Shilpa, has just submitted her thesis, and she's going to Germany for her postdoc next month. And Shobhan will be submitting his thesis this year. And we have Sharnabho, Yashika, and Aishwarya is working on experiments on quantum technology with Rydberg atoms. And we have Kirti from ISRO, who has just finished her thesis. And she was working on the optical tweezer for single atom trapping, which I'll talk about in a few slides from now. And we have a very strong theoretical collaboration. We have in-house theorist at Raman Research Institute, Shobhan Datta, with whom we collaborate. And also we collaborate with Rajesh Nath from IISER, Pune. So this is the picture of our This is a picture of our Rydberg experiment. I'll talk about it more in a few slides from now. So how do we detect these Rydberg atoms at very highly excited state? So we do a two-photon transition, and we use something called Rydberg magnetically induced transparency. So first we excite the atom from the ground state to the Rydberg state. To the intermediate state, and from the intermediate state we excite to the very highly excited Rydberg state. And so we have so for electromagnetically induced transparency, which is a very interesting quantum optics phenomena, and this occurs because of the destructive quantum interference between two transition probabilities. So here we have a ladder kind of system, and we have so here we have a ladder system, and so we have two transitions, and we have the first transition, which is going from the ground state to the Rydberg state, and then we have from the excitation from the Rydberg intermediate state to the highly excited Rydberg state. Now, electromagnetically induced transparency happens because of the destructive quantum interference of the transition probabilities of these two transitions. And so then we have, so as you can see, there's this dotted line. So this will occur when you have only one of the transition, say from the ground state to the intermediate state. And when you have the other transition, there's this destructive quantum interference, and this leads to complete cancellation of absorption. And this gives rise to the Rydberg electromagnetically induced transparency signal. And this is what we use for detecting the Rydberg atoms. So this is the Rydberg EIT signal, or Rydberg electromagnetically induced transparency signal. And this we use for detection of atoms in the Rydberg state. So this you can see, we have got this Rydberg EIT signal after subtracting the background, and this leads to a flat background EIT signal on a flat background. So before I go to our next work, which we did with the Rydberg atoms, so I would give you a short introduction to this work. So when I was doing my postdoc in Paris, I happened to hear a talk by Theodore Hansch, and he was telling in his talk that when he went for his postdoc in Stanford, in the group of Arthur Shallow, who was the co-inventor of laser. So a piece of very important advice he got from Shallow is that always measure frequencies. And this he took quite seriously, and this led to his invention of the optical frequency comb, for which he got the Nobel Prize in 2005. And keeping in mind this very important piece of advice, we did our next work on measuring the transition frequencies to very highly excited Rydberg states. So when we started this experiment, we didn't have the frequencies to which we would like to tune our lasers to excite to very highly excited Rydberg states. So we thought that the best way to measure those frequencies, to get those frequencies, is to measure it ourselves. So we measured the transition frequencies to very highly excited Rydberg states from n equal to 45 to all the way to n equal to 125. With an accuracy of less than 2 megahertz. So here you can see that these are the experimental data, and we have fitted with the theoretical prediction. And from that, we have also obtained very accurate values of what is called quantum defect. So this characterizes the deviation of this Rydberg atoms from the hydrogen-like behavior. So this happens because of the penetration of this orbitals to the inner electronic core of the Rydberg atoms, resulting in incomplete screening of the ionic charge by this inner electronic core. And this is more prominent for lower values of the angular momentum quantum number. So we got very accurate values of quantum defects with this measurement from our measurement of the transition frequencies to very highly excited Rydberg states. And we also obtained the ionization frequency of the intermediate state. So next I'll talk about what we did for quantum sensing using this very versatile Rydberg atoms. So we did Doppler-enhanced quantum magnetometry with the Rydberg atoms. So when we were measuring this transition frequencies to very highly excited Rydberg states, we were seeing a signal which we were not able to explain. So generally we use these two excitation lasers with in a counter-propagating configuration. And counter-propagating configuration, which is like the conventional way of obtaining this Rydberg EIT. And so when we got the signal, we figured out that this extra signal was coming because some back reflection from the glass cell. And this was giving rise to a proper co-propagating, the coupling laser in a co-propagating configuration with the probe laser, which was like a non-traditional configuration for getting the Rydberg EIT. And so we thought about understanding it better. And so we put a magnetic field here on the atomic ensemble. And to our surprise, we found that the co-propagating configuration, the Zeeman splitting in the co-propagating configuration, was an order of magnitude larger as compared to the Zeeman splitting in the counter-propagating configuration, which is like the traditional or the conventional way of getting the Rydberg EIT signal. And so to understand how this was happening, we did a theoretical modeling and we got an excellent agreement of our experimental measurements with our theoretical modeling. And this we could explain both for a linear and the circular polarization. So next I'll go to the next part of the talk, which is quantum information and sensing with cold Rydberg atoms, which is the main focus of our experiment. So we realize cold atoms in our experiment, and so here you can see that this is the picture of our cold atom setup, where we realize a cloud of cold atoms at around 80 microkelvin temperature, which is like 1,000,000 times lower temperature than the room temperature atoms. And we have two complementary detection systems to see these cold atoms and also the Rydberg excited cold atoms, which is the EMCCT camera and also the avalanche photodiode, which can detect a few photons. So we have a single photon detector module, which can detect a few photons. So we have this two complementary detection system by which we can detect the cold atoms. So to have the Rydberg excitation in cold atoms, we have this probe and the coupling laser to do the Rydberg excitation. And here you can see we get this signal from the Rydberg excitation of cold atoms. And so this is what is called a Ortler-Towns splitting from the cold Rydberg atoms. And this happens because of the AC Stark shift, which is caused by the strong, cooling laser beams or the 780 laser beams. And we use the coupling laser at 480 nanometer to actually detect this Ortler-Towns splitting. And so this is the first and presently the only cold Rydberg atom experiment in India. So, and this opens up important avenues for exploring quantum technology with cold Rydberg atoms. So we went a step further and we measured the effect of interatomic interaction in this Ortler-Town splitting in cold Rydberg atoms. So as I said that larger the principal quantum number, larger is the interatomic interaction. So here you can see that as we go from n equal to 35 to n equal to 55, there's a broadening in this signal. And this happens because of the increase in the interatomic interaction, because the interaction increases with the principal quantum number n. So this broadening is happening because of the dephasing effect of this interatomic interaction. And we have also seen signatures of Rydberg blockade. And so we are also doing the theoretical modeling to understand this experimental data better. And so we are going to explore further in going to the blockade regime and doing quantum entanglement with this cold Rydberg atoms. So another experiment which we are planning is to load this cold Rydberg atoms in a one-dimensional dipole trap. And because of the Rydberg blockade effect, we expect a crystallization happening in this 1D dipole trap. And from this crystallization, we can actually look at the scaling behavior of the fraction of the Rydberg excitation as we go to higher and higher principal quantum number. So this is one of the experiments we are planning in our cold Rydberg atoms. So since we have to work with cold Rydberg atoms and do very precise measurements with this cold Rydberg atoms, we need these two lasers which are exciting to the Rydberg state extremely stable, and that's why we are locking these two excitation lasers to a reference cavity. And after we lock it to this reference cavity, we expect a very, very stable laser system, and which will have minimum fluctuation, and this can reduce the decoherence in the system, and it will be ideal for doing quantum computation and quantum sensing with this cold Rydberg atoms. So these are the various modes we have obtained while we are optimizing the cavity. So this is our experimental data for the various cavity modes, and these have very good agreement with the simulated modes of this cavity. So here you can see just by changing the alignment of this beam inside the cavity, we can explore different modes in this reference cavity. So the next step in our experiment is to do single atom trapping for Rydberg excitation. So the idea is to have a dipole trap beam focused at very, very small focal spot of 1 micron. And then we have this cold atomic cloud, which I showed, as a reservoir, and we would want to trap a single atom in this optical tweezer from this reservoir of cold atoms. And so we will have a dipole trap beam at 850 nanometer. And we'll focus this dipole trap beam to a very small focus spot of 1 micron. And this very small focus spot will ensure that if there are more than one atom in the trap, they will both undergo inelastic collisions and both will go out of the trap. So there will be either 0 or 1 atom in this optical tweezer. So this will ensure single atom trapping in the optical tweezer. So for that, we have very high numerical aperture lenses inside our vacuum chamber. And so this enables having an optical tweezer with a very small focal spot for single atom trapping. So the importance of looking at single quantum system is evident from the fact that the Nobel Prize in 2012 was awarded jointly to Serge Haroche and David Vineland for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So we have made significant progress towards having single atom trapping. And we have already, measured submicron focal spot size with our dipole trap beam. We have measured a focal spot size of 0.92, and this ensures that we can have single atom trapping in our optical tweezer. And we have also demonstrated an array of this optical tweezer where we can trap individual atoms. So let's look at the future directions of this experiment. So our future plans in this experiment with cold Rydberg atoms is to do quantum information and quantum sensing with this cold Rydberg atoms. So the idea is to have individual atom trapped in an array of this optical tweezer, and then do the Rydberg excitation of this individual atoms in this optical tweezer and create quantum entanglement between pairs of this individual atom. And then the idea is to make using the quantum entanglement by a Rydberg blockade to create a scalable quantum network using this individual Rydberg atomic qubits in this array of optical tweezer. So we all know that in the microscopic system, it follows single particle physics, and in a macroscopic system, it follows many body physics. But what happens in the regime which is in between the microscopic and the macroscopic regime, which is the mesoscopic, and how the microscopic properties give rise to the macroscopic properties in a system. So the answer lies in exploring the mesoscopic regime. So how the microscopic properties can give rise to when scaled to macroscopic size gives rise to the many body physics of the system. So Rydberg atoms being giant atoms are ideal for exploring this very intriguing and very interesting mesoscopic regime to see how the microscopic properties give rise to the macroscopic properties or the many body physics in such systems. So the idea is to do atom by atom assembly and go from the microscopic regime to the mesoscopic regime, and then build a large scalable array of a 1D or a 2D array of this individual Rydberg atoms, and explore the many body physics in such systems. So we can arrange this individual Rydberg atoms in triangular or square array of Rydberg atoms, and look at antiferromagnetic ordering in such a system, and address open questions in quantum magnetism. Another direction which we would like to explore in our experiment is to combine this long-range interaction of Rydberg atoms with disordered potential and look for new quantum phases in such a system. Such systems have not been explored elsewhere, and we would like to explore such a very interesting and novel system in our experiment. So, as I had mentioned that Rydberg atoms are extremely sensitive to small electric fields, both DC and AC, and hence they are very promising candidates for quantum sensing and metrology. So the idea is to have a individual Rydberg atom in the optical tweezer, and then use this individual Rydberg atoms to do quantum sensing, very sensitive quantum sensing of external electromagnetic fields. And Rydberg atoms don't need any calibration, unlike other probes where the accuracy depends on how accurately you're calibrating your probe. But Rydberg atoms are, the same everywhere in the universe. So they don't need any calibration. So we would like to use individual Rydberg atoms for quantum sensing to get very accurate measurements of external electromagnetic fields. So we can choose the energy levels of the Rydberg atoms to do the quantum sensing of either microwave or terahertz fields, depending on which energy levels we are choosing. And we can go to the state-of-the-art accuracy of quantum sensing, which is at present 10 microvolt per centimeter per square root of hertz. And by doing quantum sensing and metrology using Rydberg atoms, we can using individual Rydberg atoms, we can beat the standard quantum limit via quantum tricks such as squeeze states and reach the Heisenberg limit. So, as I've mentioned, with Rydberg atoms, we can explore the various regimes of quantum technology like quantum computation, quantum simulation, quantum sensing and metrology. We can do quantum simulation of complex solid-state system. We can do ultra-fast quantum dynamics, and we can also make a futuristic dipole antenna for observational astronomy. So you can see that cold Rydberg atoms are really a versatile platform for exploring the various regimes of quantum technology. So I come to the end of my talk. So I gave an introduction to quantum technology with Rydberg atoms, and then I talked about various or a few of the very exciting results we have got in our lab using Rydberg atoms, and I talked about a few of the future perspective on quantum information and quantum sensing with cold Rydberg atoms. And so I come to the end of my talk, and we can have some assignment problems. For example, you can work out how we have this various dependence of the properties of the Rydberg atoms on the principal quantum number, that how do we get the radius as n square, how do we get the radius of lifetime as n cube, how do we get the polarizability as n to the power 7, how do we get the dipole-dipole interaction as n to the power 4, and the van der Waals interaction as n to the power 11. So this is your assignment. You should work out, and it will be very exciting to find out how Rydberg atoms have, such a very strong dependence on the principal quantum number, and how Rydberg atom gets its exotic properties, which makes it so promising for quantum technology application. So thanks very much for your kind attention.